Ever just look around and think about all the stuff, all the things around you?
Yeah.
You've got like your phone,
Right.
right? And it's all smooth and sleek.
Right.
Then there's maybe a wooden table, rough and kind of grainy,
Yeah. Yeah.
and maybe a soft blanket or something else totally different.
Uh-huh.
Makes you wonder, doesn't it? What's all this stuff made of?
Yeah, what's that basic fundamental stuff that makes up, well, everything?
Like, if we zoom in, weigh in, what are we really dealing with?
Well, that's the question that scientists and philosophers before them have been asking forever.
Right, forever. So today we're going to take a deep dive into this idea of matter.
Yeah, the scientific concept of matter.
The real nuts and bolts.
The building block.
Exactly. And we're going back to basics, back to the source.
Yeah.
Like chapter 1 of a science textbook.
Yeah, the real foundation.
So we can really understand how scientists think about what makes up the world.
All the stuff we see and touch.
But we're going to focus on the physical stuff today, the physical characteristics.
Right, the tangible aspects of matter.
We'll save the chemical reactions and all that for another time.
Keep it nice and focused.
So just to give you some historical context, our sources mention these early Indian philosophers.
Really fascinating.
They had this idea called the Panch Tattva,
Yeah, it's beautiful, actually.
which basically means 5 elements: air, earth, fire, sky, and water.
5 fundamental elements that they thought made up everything.
The whole universe.
Yeah, pretty cool, right?
Super cool. And it's not just them. Ancient Greek philosophers also had their own ideas about fundamental elements.
Uh-huh.
It's so interesting to see how people have been trying to figure this out for ages.
Yeah, trying to understand the essence of reality.
And now, with modern science, we've gotten a much clearer picture.
More refined, definitely.
Yeah, but it's built on all those earlier ideas.
Absolutely.
So how do scientists now classify matter?
Well, there are 2 main ways, based on physical properties and chemical nature.
And today, we're diving deep into the physical stuff.
That's our focus.
So our mission for this deep dive, for you listening, is to really grasp the physical nature of matter.
That's it.
We'll start with this big question.
Yeah.
Is matter continuous or made up of tiny particles?
Big question.
Then we'll try to wrap our heads around just how small those particles are.
Mind-bogglingly small.
We'll look at their characteristics, how they behave.
And how those behaviors create different states of matter.
Exactly, like solid, liquid, gas.
The forms we see.
And we want to do this in a way that's easy to understand,
Jargon.
but still really insightful.
Yeah, like those aha moments.
Okay, let's jump right into it.
Let's do it.
Continuous versus particulate. That's our first big debate.
Is matter like a smooth block of wood that just goes on and on?
Right, just continuous, no breaks,
Or is it like a pile of sand?
with tiny individual pieces.
Lots of tiny pieces.
That's what particulate means.
Exactly.
So to figure this out, our source starts with a simple experiment.
Activity 1.1.
It's so simple, but so clever.
Elegant.
Okay, imagine this. You've got a glass beaker.
Standard science equipment.
You fill it with water and mark the water level.
So you know exactly where it is.
Then you take a spoonful of salt or sugar,
Something that dissolves easily.
stir it in until it
Oh,
completely
that's-
disappears.
You can't see it anymore.
Now here's the key question.
Yeah, pay attention.
Did that water level change?
And if so, by how much?
What do you think?
Take a moment to consider.
Would adding something make the volume go up?
You'd think so, right?
It seems logical.
But here's the thing.
The water level doesn't change that much, if at all.
It's subtle.
So what's going on?
It's not like that salt or sugar just vanished into thin air.
Right, it has to be somewhere.
It spreads out in the water, but at a level we can't see.
Invisible to our eyes.
But the volume barely changes.
So this tells us something crucial.
It's a big clue.
The salt or sugar must be breaking down into incredibly tiny pieces.
Way smaller than we can see.
And these tiny pieces are fitting into the spaces between the water particles.
Sneaking in those gaps.
Figure 1.1 in our source shows this really well.
Visual aid.
So matter isn't continuous, it's particulate.
Made of tiny bits with spaces in between.
Okay, so we're talking particles, but how small are these particles?
Well, Activity 1.2 is designed to blow your mind.
This one's a classic.
And it's visually stunning.
You start with just a couple of tiny crystals of potassium permanganate.
They're this really intense purple color.
You dissolve those crystals in 100 milliliters of water.
Turns the water this amazing deep purple.
Then you take just 10 milliliters of that purple solution
A small fraction.
and add it to 90 milliliters of clear water.
So you're diluting it.
And you repeat that process like 5 to 8 times.
Diluting, diluting, diluting.
Each time, taking a little bit of the colored water and adding it to more clear water.
What do you think happens?
What do you think happens to the color?
Does it disappear?
Well, even after all that diluting,
Like a lot of diluting.
the water is still visibly pink or light purple.
It's incredible.
You started with just a few tiny crystals, and they colored a huge amount of water.
Amazing.
It means those crystals must contain an insane number of particles.
Mind-blowing numbers.
So small, they can keep spreading out and still have an effect.
Our source also mentions you can do something similar with Dettol.
You know, the antiseptic liquid?
Yeah, just a tiny bit.
And even after diluting it tons of times, you can still smell it.
Crazy, right?
Shows just how small these particles are.
Like our source says, small beyond our imagination.
Okay, so matter's made of these super tiny particles.
Now, what are they like?
What are their characteristics?
Well, first of all, there's space between them.
We saw that in Activity 1.1, right?
Yeah, when the salt or sugar disappeared into the water.
It's also how we make tea or coffee.
Or lemonade, anything you mix.
The particles of one substance fit into the spaces between the particles of the other.
It's like a microscopic puzzle.
So matter isn't totally solid.
There's emptiness.
Tiny gaps everywhere.
Makes you think, doesn't it?
It really does.
Okay, second characteristic. These particles are always moving.
Never still.
They have what's called kinetic energy.
The energy of motion.
And we can see this in action with a few simple experiments.
Let's try Activity 1.3. The incense stick.
Oh, yeah, I love this one.
If you have an unlit incense stick, you got to be close to smell it.
True.
But light it up.
And whoosh.
You can smell it all over the room.
Yeah, travels fast.
Why? Because the heat from the flame gives the smoke particles more energy.
More energy, more movement.
They move faster and spread out quicker.
So heat really affects particle motion.
Absolutely.
Now, let's look at Activity 1.4, ink and honey in water.
Okay, 2 beakers, one with water and a drop of ink, one with water and a drop of honey.
Watch carefully.
What do you see?
The ink spreads and mixes much faster than the honey.
Why is that?
Well, both ink and honey are made of moving particles.
They'll both eventually diffuse into the water.
But honey's thicker, more viscous.
The particles are more resistant to movement
They're slugger.
compared to the ink particles.
So even in liquids, particles move, but at different speeds.
Depends on the substance.
Exactly.
Okay, last one for this point. Activity 1.5.
We're going back to temperature.
Take a crystal of copper sulfate or potassium permanganate.
Colorful crystals.
Drop one in hot water, one in cold water.
What happens?
You'll see the color spreads much faster in the hot water.
Way faster.
Because the heat gives those particles more energy, they move faster.
Temperature and kinetic energy are linked.
So heat isn't just about feeling warm,
It's about energizing particles.
making them move and groove.
So this brings us to diffusion.
Our source defines it as the intermixing of particles of different substances.
They mingle and spread out.
And heat speeds up diffusion.
Acts like a catalyst.
All right, so far we've got space between particles. Particles are in constant motion.
What else?
What's the third big characteristic?
There are forces of attraction between particles,
Like an invisible glue.
holding them together.
But the strength of the glue varies.
Let's try some activities to see this.
Activity 1.6 is fun.
You need some friends for this one.
Divide in 4 groups.
Teamwork.
3 groups make human chains.
Link up.
Group 1, lock arms tight.
Strong bond.
Group 2, hold hands.
Looser connection.
Group 3,
Mm.
fingertips touching.
Barely there.
Now, the 4th group tries to break each chain.
Let's see the strength.
Which one breaks easiest?
What do you think?
Yeah, the fingertips chain.
Weakest connection?
Why? Because the force holding them together is the weakest.
Just like with particles.
Some substances have strong attraction, some weak.
It's all about those interparticle forces.
Okay, activity 1.7, breaking stuff.
This is satisfying.
Get an iron nail, a piece of chalk, and a rubber band.
3 very different solids.
Try to break them.
Hammer, cut, stretch, whatever works.
Which is the hardest?
Like you can guess.
The iron nail, right?
Strong forces between those particles.
The chalk breaks easily.
Weak forces.
And the rubber band somewhere in between.
It can stretch and return to its original shape.
Show some flexibility.
Yeah, but too much force and it snaps.
Last one, activity 1.8, water in your finger.
Simple but cool.
Get a bowl of water, try to cut the surface with your finger.
What happens?
You can't really cut it clean.
Nope.
The water just flows around your finger.
Like a magic trick.
This shows there are attractive forces between the water particles at the surface,
They hold together.
like a thin, flexible skin.
They don't want to separate.
So our 3 key particle characteristics are
Go ahead, Axaba.
space between them, they're always moving, and there are forces of attraction.
Perfect.
And these characteristics determine the state of matter.
Solid, liquid, or gas.
Let's start with solids.
The rigid ones,
Our source has us think about everyday solids.
pen, book, needle, wooden stick.
They all have a definite shape,
You can describe their boundaries clearly.
and they have a fixed volume.
They take up a specific amount of space.
What if you try to change their shape?
Hammer them, pull them, drop them.
They resist.
Right.
They want to keep their shape.
Unless you use a lot of force, then they might break.
Can you compress a solid?
Squeeze it down into a smaller space.
Not really.
Negligible compressibility.
So solids are
Let's sum it up.
definite shape, distinct boundaries, fixed volume, and rigid.
They hold their form.
But our source throws in some curveballs,
To make us think.
like a rubber band.
You can stretch it.
Does that mean it's not a solid?
Good question.
And sugar, or salt crystals.
When you pour them, they take the shape of the container.
So no fixed shape.
Hmm.
And a sponge, you can squeeze that.
It gets smaller.
How is that a solid?
These are good points.
But they actually make sense.
Let's break them down.
The rubber band, it stretches, but it goes back to its original shape.
Unless you break it.
So it still has that tendency to maintain its form.
Experiment shape.
Sugar and salt crystals, they do have a fixed shape.
But it's at the individual crystal level.
Each tiny crystal has a specific shape.
But a pile of them takes the container shape.
Makes sense.
And the sponge, it's tricky.
Seems compressible.
But it's because of the air trapped inside.
Those little holes,
When you squeeze, you're pushing out the air.
the solid part of the sponge is still rigid.
Maintains its volume.
So even with these exceptions.
Solids still have those key properties.
Okay, let's flow into liquids.
Smooth transition.
Think about water, oil, milk, juice, any liquid.
What happens when you pour them?
Activity 1.10 wants us to visualize this.
Pouring, spilling, transferring.
What do you notice?
First, liquids have no fixed shape.
They take the shape of their container,
Totally adaptable.
but they do have a fixed volume.
If you pour 50 milliliters into different containers, it's still 50 milliliters.
And they flow.
Easily.
That's what makes them liquids.
Unlike solids, they're not rigid.
They're fluid,
Let's talk about diffusion again.
how things mix.
We saw that solids and liquids can diffuse into liquids.
Remember the ink and honey?
Yeah, and our source mentioned something crucial.
What's that?
Gases from the atmosphere, like oxygen, can dissolve in water,
It's how fish breathe.
essential for aquatic life.
And liquids diffuse faster than solids, right?
Why do you think?
Because the particles have more freedom to move around.
More space between them, too.
Easier to intermingle.
Exactly.
Okay, last state. Gases.
The invisible ones.
We see gases in action all the time.
Like those balloon sellers.
Filling tons of balloons from one cylinder.
So much gas in a small space.
Or when you smell food cooking from another room.
It spreads fast.
To demonstrate this compressibility, let's do activity 1.11.
Syringe time.
Get 3 syringes.
Yeah.
One with air, one with water, one with chalk.
A gas, a liquid, and a solid.
Try to push the plungers in.
How do you feel?
The air syringe compresses easily.
You can really push it down.
The water, not so much.
Much harder.
And the chalk, practically impossible.
That plunger's not budging.
This shows the gases are highly compressible.
Compared to liquids and solids.
And this has tons of applications.
Yeah, real world stuff.
Like LPG cylinders for cooking,
Compressed gas.
oxygen tanks in hospitals,
Life-saving.
CNG vehicles.
Alternative fuel.
Being able to compress gases is super useful,
And that quick spread of smells.
like the cooking aroma.
That's because gas particles move really fast.
And there's a lot of space between them.
So they diffuse quickly.
And then there's pressure.
Gases exert pressure.
It's all those particles constantly colliding with each other, and the container walls,
We're bumping around.
more collisions, higher pressure.
So to sum up gases, no fixed shape, no fixed volume, highly compressible, diffuse quickly, and exert pressure.
Okay, we've covered the states of matter.
But can matter change states?
We all know water can be ice, liquid, or steam.
The classic example.
But what's happening at the particle level during these changes?
What's going on in those tiny worlds?
And what causes these transformations?
Let's explore.
Our source looks at temperature and pressure.
Two big factors.
Let's start with temperature.
Heat things up, cool them down.
Activity 1.12. Heating ice in a beaker.
Classic experiment.
As you heat the ice, the temperature rises
Watch that thermometer.
until it reaches the melting point.
0 degrees Celsius for ice,
Then the ice starts melting.
turning into liquid water.
But here's the weird part.
Yeah, pay attention.
Even though you keep heating, the temperature stays constant
Stays at 0 degrees.
until all the ice is melted.
Then it starts rising again.
Same thing happens when you boil water,
Temperature plateaus at 100 degrees Celsius.
while the water turns to steam.
So why those temperature plateaus?
Why doesn't the temperature keep rising?
It's because the heat energy is being used for something else.
Not to increase the temperature,
It's being used to overcome the forces holding the particles together.
breaking those bonds.
So from melting, the heat makes the water molecules in the ice vibrate faster and faster
Kinetic energy.
until they break free from their fixed positions in the ice.
And start moving more freely as a liquid
The melting point is the temperature where this happens.
at a given pressure.
Right, pressure matter.
And this whole process of solid to liquid is called fusion.
Melty goodness.
And that temperature plateau during melting,
The seemingly hidden heat.
that's the latent heat of fusion.
The energy needed to change the state, not the temperature,
It's the amount of heat needed to melt 1 kilogram of a solid
at its melting point.
without changing the temperature.
So liquid water at 0 degrees Celsius actually has more energy than ice at 0 degrees.
Because of that latent heat.
It took energy to break those bonds.
Okay, boiling is similar.
You keep heating the water, the molecules move faster and faster
Until they have enough energy to completely escape the liquid.
and become a gas.
So boiling point is the temperature where this happens.
For water, it's 100 degrees Celsius at normal pressure.
And just like melting, there's a latent heat of vaporization.
The energy needed to turn a liquid into a gas at its boiling point.
So steam at 100 degrees has more energy than water at 100 degrees.
Because it took extra energy to break those final bonds.
Our source also mentions a Kelvin scale.
Another way to measure temperature.
To convert from Celsius to Kelvin, you just add 273.
Easy peasy.
So the main takeaway here is that changing the temperature can change the state of matter.
Heat it up, cool it
gravity.
down, things transform.
But our source also talks about skipping states.
What?
Yeah, some substances can go straight from solid to gas
Or gas to solid.
without ever becoming a liquid.
That's wild.
It's called sublimation, when a solid turns directly into a gas,
Sounds like a magic trick.
and deposition, when a gas turns directly into a solid.
Reverse magic.
Activity 1.13 shows sublimation with camphor.
That stuff with a strong smell.
You put some in a dish, cover it with a funnel, and heat it gently.
Watch closely.
The camphor disappears without melting,
Poof!
and then it reappears as a solid on the cooler part of the funnel.
Solid to gas, back to solid.
No liquid in between.
Amazing.
Another example is dry ice.
Solid carbon dioxide.
It's stored under high pressure.
And when you release the pressure,
It goes straight to gas.
no melting, no puddles.
That's why it's called dry ice.
so cool.
Your temperature can change states, sometimes even skip states.
What about pressure?
Can pressure change the state of matter?
Remember how we described the states in terms of particle spacing?
Solids, particles close together, liquids
Yeah.
a bit further apart, gases far apart.
So if you compress a gas, squeeze it down.
You're pushing those particles closer.
Figure 1.8 in our source shows this visually.
The question is, can you push them close enough to change the state?
Can you force a gas into a liquid or even a solid?
The answer is yes.
Pressure is powerful.
By increasing pressure and decreasing temperature, you can liquefy gases.
Think about those gas cylinders.
They contain gases that have been compressed,
Squeeze into a small space.
and dry ice is a solid because it was formed under high pressure.
So pressure and temperature work together to determine the state of matter.
Figure 1.9 shows this really well.
A diagram of state changes.
Okay, last topic, evaporation.
Sounds like boiling, but it's different.
Both involve liquid turning into vapor.
But evaporation happens below the boiling point.
Think about a glass of water left out.
It slowly disappears.
Even though it's not boiling,
Or wet clothes drying on a clothesline.
that's evaporation.
So what's happening?
Our source says that even below boiling, some liquid particles have enough energy to escape the surface
They break free.
and become vapor in the air.
It's a surface
It
phenomenon.
happens at the top layer of the liquid.
And several things affect the rate of evaporation.
Activity 1.14 explores this.
Let's see what we learn.
First, surface area. Spreading a liquid out makes it evaporate faster,
More surface exposed to the air.
like spreading clothes out to dry.
Second, temperature. Higher temperature, faster evaporation.
More particles have enough energy to escape.
Third, humidity. Drier air, faster evaporation.
The air can hold more moisture.
Fourth, wind speed. More wind, faster evaporation.
The wind carries away the vapor, making room for more.
So warm, dry, windy day.
Perfect for drying clothes.
But here's the really interesting part.
Evaporation causes cooling.
What?
Yeah, when those high-energy particles escape, they take their energy with them.
leaving the remaining liquid with less energy.
And since temperature is a measure of average particle energy,
The liquid cools down,
to make up for the lost energy, the liquid absorbs heat from its surroundings.
like from your skin.
That's why sweating cools you down.
It's your body's way of regulating temperature.
The sweat evaporates, taking heat with it.
And that's why cotton clothes are good in summer.
They absorb sweat and allow it to evaporate easily.
Better cooling.
Our source also mentions why water droplets form on a cold glass.
That's condensation, the opposite of evaporation.
The water vapor in the air hits the cold glass,
Loses energy, turns back into liquid.
forms those little droplets.
Fascinating how it all works.
So we've learned so much about the physical nature of matter.
It's all about those tiny particles.
They have space between them, they're constantly moving, and they're attracted to each other.
These characteristics determine whether something's a solid, liquid, or gas.
And we can change states by changing temperature and pressure.
Even skip states with sublimation and deposition.
And finally, evaporation. It's a cooling process.
Affected by all sorts of factors.
It's incredible to think about how these tiny particles create the world around us.
Look around you with new eyes.
Can you see those particles in action?
What other everyday phenomena can you explain now?
If you enjoyed this deep dive, keep exploring.
There's always more to discover.
Maybe next time we'll tackle the chemical nature of matter.
That's a whole other adventure.
But for now, thanks for joining us on this deep dive.
Keep those brains buzzing.
Until next time.
See you then.